Right, hi, everyone. So what we're going to do is we're going to go over this bookshelf problem. This is a fun problem because it has both a greedy algorithm and a dynamic programming aspect to it. So let's get to it. So the problem we're going to do is we're going to store a bunch of books on a bookshelf. So you can see here that here are our books. Well, here are 10 books. I've already put them on the bookshelf, but you can visualize what the bookshelf looks like. The bookshelf has a thickness of L. And then we're given the lengths and widths of each book. So you can see that book 0 looks like this, book 1 looks like this, book 2 looks like this. And then we're given the length, well, not length, I guess, thicknesses and the heights of each book. We're first going to assume that all the books have the same height. The rule is we have to put the books in order. So the books 0, 1, 2, 3, we have to put them in that order. Okay, now you can move them to different shelves, but if you move them to a different shelf, then you have to also move the books after it. Okay, they always have to remain in order from left to right. So for example, I can alternatively put the books like this. Book 0, book 1, but instead of putting book 3 here, I can put book 3 on the next shelf. Okay, now book 4, even though you sort of see that there's some space over here, right? We can't put book 4 there. We have to put it in order like that. Book 5. Okay, so then the question is just how can we pack these books? All right, you have to pack these books, and our goal is to try to minimize the total height of the entire shelf. Minimize this entire height. Okay, now because each of the books have the same height, each shelf is going to have the same height. It's just going to be h. Okay, now let's try to come up with an algorithm that solves this. Okay. Now, I'm not going to go over the pseudocode for this because you have the solutions, but yeah, essentially the pseudocode to solve this is to just always stuff the next book, always try to stuff it as much as you can into the current shelf. If you can't stuff it in the current shelf, then you just put it to the next shelf, right? You don't have any choice. But whenever possible, stick the current book in the current shelf. All right, and then our goal here is we want to try to prove that that algorithm is correct because it's not really clear that that is obviously correct. I mean, it feels like it's correct, but how do you rigorously prove that? Okay, now to do that, I'm going to first use some notation and then try to give you a different view of how we're going to solve the problem. So it's true that you can solve the problem by saying, okay, book 0 goes in the first shelf, then we put book 1 on the next shelf, then we put book 2 on the same shelf, and so on. But if you try to look more macroly, what are the choices we're making? What the choices we're making is we're really choosing these C's, right? These C's represent what is the first book on each shelf. So shelf 0, the first book is index 0. Shelf 1, the first book we're gonna put is book 4, then book 7, then book 9. Right? These are the choices that we're actually making, because making these choices fixes all the other books, right? If we pick that C1 is 4 and C0 is 0, we know where books 1, 2, 3 are, right? They're in the bottom shelf. Okay, another way that we might have put the books are something like this, right? In which case, our books look like this. C0 is 0, C1 is 3, C2 is 6, C3 is 7, and C4 is 9, right? And then, so this would be the output of our algorithm as opposed to this. We want to try to find the one that minimizes the number of books, minimize the height. And because all the books have the same height, we know we're just counting how many shelves. So we want as few of these C's as we can. Okay, now let's try to prove this prove this algorithm is correct using induction. So just as a recap, recall that for proofs of correctnesses, we always use this argument, the inductive hypothesis. So let's just call that P of K. Okay, and then P of K is after algorithm makes the choices C is equal to C0, C1, to CK minus 1, there is an optimal extension. Okay, so what is the extension? The extension means you can take C1, C0 through CK minus 1, and then we're going to add a bunch of other choices. Now, these choices we have not made yet. Okay, they're in red. We have not made these choices. These are future choices to make. Okay, now what is interesting about these choices? It's guaranteed that if you make these choices, your solution will be optimal. We don't know what these choices are, but what you want to show is that you're guaranteed to find some optimal choice. Okay, some number of choices you can make so that your overall, all the choices you put, that determines the bookshelf, and then that height is optimal. Okay, what's interesting is that you want to show that even once you've made these, you can still extend the solution to get an optimal answer. That means your algorithm has not done something wrong, right? If your algorithm made a choice that made it impossible to get the optimal, then your algorithm did something wrong. You want to be able to say that after every choice you make, you can still get an optimal, right? Because what that implies is after you make all the choices, you have found an optimal, right? If you make all the choices and you still have an optimal, then that has to be the optimal, right? You're done with all your choices. You've got the optimal. Okay, so this is the inductive hypothesis. And let's just recall what optimal means. Optimal means M is as small as possible, since we're trying to use as few shelves as we can. All right, let's prove the base case. Base case is pretty simple, P of 0. So we're saying that after our algorithm has made no choices, there is still an optimal extension. Can you think about what the optimal extension would be? Okay, so yeah, we don't really know what the optimal extension is, but if we assume that there is an optimal, like not optimal extension, an optimal overall. So let's assume C0 is an optimal overall. Okay. Then obviously this C star will extend C, because you haven't made any choices. So you can just take everything in C and just put it in, take everything in C optimal and put it in C. That is an extension, right? That's saying that all this black stuff, the choice is already made. Algorithm, that's just saying that is empty. And then the future choices you would make would be C optimal, right? We show that an optimal extension does exist. If an optimal exists, then an optimal extension has to exist. So that shows that P0 is true. If optimal exists, right? Which it has to, because we're assuming that there's a solution to our problem, right? If there is no way to put the books on the bookshelf, so I guess that means that just means your books are too thick, right? If there are no ways to put the books on the bookshelf, then you're not going to find a solution. But assuming that there is a way to put the books on there, C, you have to have a optimal way to put it, C optimal, and then your C would be able to extend C optimal. Okay, let's go to the inductive step. This is where things get tricky. So remember, inductive step, you always should assume P sub k, and you want to prove P sub k plus 1. So what does that mean? Well, P sub k means that after your algorithm makes k minus 1 choices, there is an optimal extension. Okay, so suppose our algorithm makes choices. And it's made the choices C0, C1, C2 through CK. And then on the very next iteration of the algorithm, it's going to make one more choice, CK. This is the next iteration. We're assuming that in the first K iterations, so C0 through CK minus 1, there is an optimal extension, right? Which is C star equals C0, C1 through CK minus 1. And then the red stuff is just what the actual optimal extension is. Okay, we don't know what it actually is. We just assume that it exists, right? That's just the inductive hypothesis. We're just assuming that there is some extension. And what we need to show is that an optimal extension exists. after choosing CK. So we need to show that after we made these choices, including CK, that there is still some optimal extension. Right. Now, this is very common, right? When you need to do something like that. What's the most obvious thing to do? Well, we don't really know what the extension is. Why don't we just steal some from over here? Okay, so let's steal those elements. Let's just steal these elements over here. Okay, and let's call it C star star. We need to show that an optimal extension exists after choosing CK. And here, I'm claiming that the optimal extension that does exist is this thing, C star star. You just using the same reds as C star. We have to show that this is optimal and valid. Need to show C star star is optimal and valid. Okay. Now, there's a lot more notational stuff that you'll see in the written proof, but I'm just going to go over the intuition for, I'm going to use a little notation. I'm just going to go over the intuition for why it is optimal and valid. Okay. So first, why is it optimal? Well, it's optimal, assuming that it's valid, it's optimal because both C star and C star star use n+1 shelves, which means same height. So if C star is optimal, C star star is also optimal. Optimality, often pretty easy to prove. Now let's talk about proving that it is valid. This is usually trickier. And the way that we do that is we need to prove that C star star is valid. So let's write C star star again. Let's use a new page. Too bad I can't just copy it down here. So C star star is this thing. C0, C1 through CK-1, CK+1 star through CM star. The old C, or C star, was C0, K-1, and then K+1 star to CM star. All right, so we know that C star is valid. What does valid mean? Well, if it's a valid way to put the books on there, that means that, well, first thing, these are in increasing order. Okay, so yeah, that's definitely something that's important because it needs to be increasing order, otherwise the books aren't in order. Okay, second thing is that if you summed the thicknesses of the books between each shelf, they will be optimal. So I'm going to draw this just to mean the sum of thicknesses in this shelf, right? So this is, remember, C0 is the first book on shelf 0, C1 is the first book on shelf 1. So the sum of the books between them, including C0, not including C1, would be all the books on the first shelf. And that has to be less than or equal to L. Okay, and same for all the pairs, right? Every single pair of these, since it's optimal, all these are less than or equal to L. Okay, can we say the same thing about C star? Is the sum of the thicknesses of the books in each shelf also optimal? Well, we know that the books between C0 and C1 are less than or equal to L. So we do know that this is less than or equal to L. And notice that we can make the same claim pretty much about every shelf, right? Because it's almost identical to C star, right? C star star is almost identical to C star. The only thing that is different is these. Because we changed from CK star to CK, it's not clear whether or not, if you added up the books between CK-1 to CK, is that optimal? And if you added up the books between CK and CK+1 star, is that optimal? Okay. All right, so let's try to prove. So now we need to prove need to prove that the sum of the thicknesses of the shells between these two are less than L and between these two are less than L. Let's first prove this first one. Okay, and it's not really a proof, it's just an explanation. Why is the sum of the thicknesses of the books between CK minus 1 and CK, why is that optimal? Why is not optimal? Why is that less than or equal to L? The reason is because think about what CK minus 1 and CK are. CK minus 1 is a choice that our algorithm made. Then our algorithm made another choice, CK, right? Our algorithm is not going to choose a CK unless, right, all the books before CK, so CK, like the book right before CK, unless that book fit into the previous shelf, right? All the books from CK minus 1 all the way but 2, but not including CK, all those books have to fit in one shelf because our algorithm chose CK minus 1 and CK, and our algorithm always checks if it fits before it sticks the book in there. So that's why the interval between CK minus 1 and CK, that is why this is less than or equal to L. Because our algorithm chose it, and our algo checks if it fits. All right, now let's look at the other interval. This one's a little trickier. So what we do here is let's compare it to the same interval above. Let's compare it to this interval. So we're going to compare this interval with this interval. The claim is that this one, the interval between here, there are fewer books than this one. Okay, now if that was true, then it's easy, right? Because if it's a top one, if this top one has more books, and if you added up the lengths of all the books on that shelf, if that's less than or equal to L, then this one must be less than or equal to L too, because it has fewer books. So let's think about why the bottom one has fewer books. How is CK chosen? Right, our algorithm always tried to pack as many books as possible into the previous shelf. Okay, so imagine two different scenarios. One is done by an algorithm, one was done by a human, someone else who was trying to pack the books. In both instances, we have both packed CK minus 1 as the first book of that shelf. And then our algorithm packs as many books until we get to CK. While you, the human, tries to pack some books, but maybe you won't try to pack as many as possible. Okay, so because CK is packing as many books as possible, we know that CK has to be greater than or equal to CK star. Right, CK is the index of the book on the next shelf. Because we packed as many books as possible into that previous shelf, CK is going to be large. It's going to be larger than if we packed CK plus star. Okay, let me just draw a picture so you can imagine. Let's say our algorithm was packing books 10, 11, and 12, and then it tried very hard and it tried to pack 13 and it fit perfectly. Then 14 goes on the next shelf and so on. While you, as the human, you didn't try too hard. You said pack 11, pack 10, pack 11, pack 12. And then 13, you're like, you know what? I'm just going to put it on the next shelf. Right? Because our algorithm always packs as many as possible. If you compare the CK, so this is the CK. Well, this is CK star. This is the supposed optimal by the human. 14 is greater than 13 because our algorithm tried really hard to pack as many books as possible. So that index that you see over there needs to be larger than if we had just done it in some other way. Okay. All right. So because that is the case, we know that there is on the bottom one, that purple circle, there are fewer books in that circle than the books in the top circle, right? It's basically the exact same books, but some of the books were moved to the bottom shelf because our algorithm tried to pack as many as possible. So because of that, we know that the bottom one has fewer books than the top one. So if the top one has sum of length thickness is less than or equal to L, then the bottom one also has sum of thicknesses less than or equal to L. Okay, so this shows so we've shown that all shelves in C star star have length less than or equal to L. We also have to show that it's increasing, and that's easy because so C star is valid. So all the books, so the C's in this order are increasing. We know that in the bottom one, the first up to CK are increasing. Our algorithm chose CK, so that has to be greater than CK plus minus 1, right? We know that everything else after that is increasing because above, everything in the red is increasing. So we just have to show that CK plus, we just have to show that CK plus 1, we need to prove CK plus 1 star is greater than or equal to CK. Okay, and how can we prove that? Well, we know that CK star is less than or equal to CK plus 1 star, since C star is valid. And then we also know that CK is less than or equal to CK is greater than or equal to CK star. Did I write this correctly? I'm trying to prove that CK is CK. We're trying to show that CK plus 1 star is greater than or equal to CK. And then we know that CK star is, okay, we know that is true. Does this help us? CK has to be greater than or equal to A star. All right. Let's see. I think I'm missing something here, so let me just double check. But yeah, there should be a way to prove that CK plus 1 is greater than or equal to CK. Okay, yeah, because once you prove that, you've proven that this is also increasing, so you know that the entire C star star is increasing. Okay, all right, and that concludes the proof, showing that they have less than or equal to L, and C star star is increasing. So C star star is valid, and we've also shown that it's optimal, which shows that C star star is just as valid and just as optimal as C star. Okay, and that concludes the inductive step. The conclusion, P sub k is true for all k greater than or equal to 0. And then this is the important part. In particular, P of m minus 1 is true, okay, where m is number of bookshelves used. Okay, so what does that mean? That means after you pick, I guess P of m, after you have picked every single bookshelf, right? The inductive hypothesis says that there is still an optimal extension. So after you have picked C0, C1, all the way to Cm, there is still an optimal extension, C star, which is C0, C1, Cm, right? Well, we're at M already, so there's no more of those stars. Well, if this is an optimal extension, that's the same thing as C. So if C star is an optimal extension, then C has to be optimal. That proves that this C that our algorithm chose is optimal. And that's how you prove that a greedy algorithm is correct. Okay. All right. So I'm going to stop the video now. There is a dynamic programming section to this. I might make a video about it later, maybe during the exam review. But the important part of this video was to try to show that this greedy algorithm is correct. Okay. All right. See you next time. I'll make another video on the next problem. as well.